Hello everyone and welcome to day 36 of the Jamb Physics in 40 Days series. I want to say a big thank you to all of you that has been part of the series from day 1. This is day 36 and in just a few more days we will get to the end of this series. I want to believe that you've learned a lot from the series so far, and I want to trust that you are not enjoying this all by yourself. So I want to say thank you for sharing the videos, thank you for liking the videos, thank you for making it a date with the series every day from day 1. You are the real MVPs. So thank you so very much. The series still continues and there's still a whole lot more to do. The 36 is packed with a lot for you, so I hope that you're ready for what we're about to go into. Now, if you're seeing this video for the first time, this is Jamb Physics in 40 Days series. It is brought to you by Oya Learn, where we believe that when you are able to dedicate within 30 to 45 minutes of your time daily, you should be able to get all the tools that is necessary for you to ace Jamb Physics. So peradventure, you are preparing for the next Jamb exams, and amongst your subject combination, one of the subjects you have picked is physics. Then trust me, these videos are made specifically for you, so you want to check it out from day 1 to the end. You don't want to miss any of the videos in this series. What we have been able to do is that in each of the videos, we'll look at the individual topics in the Jamb Physics curriculum, and then we do a breakdown just like this, where we touch everything that is expected of the candidates before the exams, and then we go on to solve past questions on those topics while giving you some tips that help you to solve questions like that with great accuracy each time you find them. So there's no way you will go through this series from start to end and you will not be able to ace Jamb Physics. It will become quite easy for you. So you want to check out every videos in this series, and we also urge you to improve more by practicing with the Exam Fun app. The link is added to the description box of the video. It's an app that is created to infuse a bit of fun into your learning time, where you get to solve questions on any subject of your choice at different levels, and then you earn points and even some money. So it's an app that is both exciting and rewarding. So please click the link in the description box of the video to download the Exam Fun app today, so that you too can have fun and earn while you learn. And please do not forget to subscribe to the channel. You can do this by clicking the subscribe button and also hitting the notification bell icon, so that every time we put out a new content, you will definitely be alerted. And please ensure that you like the videos and also share them, so that you can help us to reach a wide range of audience that are in need of content like this. So let's get to the business of day 36. Now, what we're going to be looking at in this video is Simple A.C circuit. This is one of the topics that a lot of you have been expecting, so we are there now. And what we'll be looking at in this topic are listed here. These are what is expected of Jamb of every candidate, the different subtopics on Simple A.C circuits that you should be able to go through. Now, the first one we have here is AC current and voltage. Now, when we talk about AC current and voltage, we are looking at an AC circuit, that is a circuit that is powered by an alternating current source. Now, what we call AC current is a type of current that it is always changing periodically. That is, it is increasing with time, just as it moves from positive to negative phase as well. So it's always changing with time. It is represented by a sinusoidal waveform. And the same thing applies to the AC voltage. It's also represented by a sinusoidal waveform, and it is a potential difference that changes periodically. That is, it changes with time. And to express this, the AC voltage E is given by the equation E equals E naught sine WT, where E naught is the maximum voltage or peak voltage. You know, just like when you draw your waveform, what you know as amplitude. So the amplitude of that waveform is the peak voltage when you are doing the voltage with respect to time on your graph. So this is the peak voltage. So let me note that here. E naught is peak voltage. Okay. And the W here can be written as 2 pi F. Okay. And the same thing applies in the case of current. I naught here will be peak current. That's the maximum current that you experience in that circuit. Remember that the current is also changing periodically. Now, beyond that, they also expect that you should be able to express what is known as peak and RMS values of voltage and the current. And they are in this equation where Vrms is the peak voltage divided by sort 2, and the RMS current is peak current divided by sort 2. Note that this can also be written as Vrms equals 0.707 V naught, because 1 over sort 2 will give you 0.707, and the same thing applies to the current. So RMS current can be 0.707 I naught as well. Now, you should also know you should go through the topic AC source connected to a resistor. Now, when you have a resistor in an AC, right, what you're going to be having there, you must take note that when it is just a resistor that is there, the voltage and the current are in phase. So as a result, the current can be calculated using Ohm's law as the maximum voltage divided by the resistance offered in the circuit. Now, this is because the current and voltage are in phase. There is no lag and there is no lead. So you can easily calculate that one using Ohm's law. So if you remember what we did during Ohm's law, V equals IR, all of those also apply in the case of AC source connected to a resistor. However, by the time you connect it to a capacitor like what we have in line 4 here, AC source connected to a capacitor, you must go through what is known as capacitive reactance. Now, this is because in an AC source connected to a capacitor, current is going to lead voltage. Now, there is this thing I use usually to explain how you can know whether current is leading or voltage is leading. There's what we call the ICE or ICE, okay, and then there is ELI. Now, ICE means current will lead the EMF in capacitor. This is for capacitors, okay, and this is inductance. So when you have an inductor, it is the EMF that leads current, but in capacitor, currents lead EMF. I believe you understand this. It can help you easily remember how they relate with each other in terms of current and EMF for capacitors in an AC source or inductor in an AC source. Now, when it comes to capacitive reactance, it is given by the equation Xc equals 1 over 2 pi Fc. Now, take note, F here is the frequency of the circuit and C here is the capacitance of the capacitor. And for inductor, the inductive reactance is XL given by 2 pi FL. F is also frequency and L here is known as the inductance, which is measured in henries. Now, sometimes you could have a circuit that combines either just capacitor and resistor, or inductor and resistor, or even the three of them in one circuit. Now, that is what we know as a typical AC circuit. It must contain either resistor and capacitor, resistor and inductor, inductor and capacitor, or the three of them at a go. So that kind of circuit is also referred to as the RLC circuit when you have the three of them. RL stands for resistance, L stands for inductance, C stands for capacitance. So when you have the three of them in a circuit, we call it a RLC circuit. Now, for this, for the purpose of this study, we are only looking at the series circuit of this. Doesn't mean that you may not want to combine them in parallel, but for this topic, we are only limited to the series circuit of RLC. So we'll be looking at what happens when you have resistor, inductor, and capacitor connected in series in an AC circuit. Now, this will lead us to finding out what is known as impedance. Now, impedance is the resistance offered by a combination of resistor, inductor, and capacitors. Now, when you have the three of them in the circuit, this is what we apply. Okay. However, if it is just resistor and capacitor, for example, you would have done R squared plus XC squared. Okay. And if it is just inductance, it will be R squared plus XL squared. Okay. However, you should know that when everything is together, we have what is called reactance. And reactance itself is inductive reactance minus capacitive reactance. That's what gives us the total reactance offered by a capacitor and an inductor in an AC circuit, which is why it is put into this equation. It's supposed to be resistance plus reactance all squared, then we take the square root of everything there. So that's how we get impedance, and then we can still apply Ohm's law in this case, but we replace the resistance now with impedance because we have capacitor and inductor in the circuit. So the current becomes EMF divided by impedance. And then you should be able to draw the vector diagrams that represent capacitors, inductors, current and voltage when they are in an AC source. And you should be able to find the phase angle and power factor. Now, phase angle is given by tan phi, which is the reactance divided by resistance. And remember I said reactance is XL minus XC, so that's what this means. So X is XL minus XC, all divided by resistance. While the power factor is known as cos phi, and that is given as the resistance divided by impedance, meaning you have to find the impedance first before you can find the power factor. And then you should also be able to calculate the resistance and impedance. I've given the equations here already. So whenever you are given those values, whether you are given the inductance, you are given the capacitance and resistance in an AC circuit, you should be able to use those information to find the resistance or to find the impedance or even the voltage in the circuit or the voltage shared. Remember, it's an AC circuit and they're going to share the EMF across each of the individual elements, that is the resistor, capacitor and inductor. You should be able to solve that. And you should be able to find the effective voltage in an RLC circuit also using the equation V equals current times impedance, where this current is the RMS value and the V is the RMS value. Now you can also replace them with peak values as well. So each of them just has to be the same. Whether you're doing RMS or peak, they just have to be the same and they apply in this manner. And then there are some cases where in an AC circuit, the inductance and the inductive reactance, rather, not inductance, inductive reactance, that is XL, and capacitive reactance XC are the same. When you have the same value of XL and XC, that is XL equals XC, such a circuit is said to be at resonance. So at that point, you have to find what is known as the resonance frequency. And the resonance frequency is given as 1 over 2 pi square root of the inductance multiplied by capacitance. So these two information will come in handy when solving questions with resonance frequency AC circuits. So that's basically about all that is expected of the candidates taking the exams. And because this is for the purpose of Jamb, we'll just only be able to talk about them. And there's a probability that I may have skipped one or two things that is very important to it. But be rest assured, as we solve questions, when we touch those kind of things, I would explain even further. However, if you want a deeper understanding of this topic, please check out the video on our channel where we talk on simple AC circuits in more detail. Now, that one will be in the playlist for the class groups, where this one is for Jamb prep. So the description is a bit different, so look out for it. Where we have simple AC circuits, we've been able to touch each of this topic with greater detail, and then I give multiple examples on each of this subtopic, and then we solve them. I also give you tips that help you understand the topic even better. But for now, we'll be solving past questions from Jamb on the topic. And while we do that, if there's anything I've missed, I will ensure to talk about them as we solve those problems. And I'll also be giving you more tips that will help you solve questions on simple AC circuits without problem. So if you're ready, get your materials and let's answer some questions on simple AC circuits. From the diagram above, if the potential difference across the resistor, capacitor, and inductor are 30 volts, 120 volts and 60 volts respectively, the effective potential difference is, now looking at the diagram, the resistor has 30 volts, the capacitor has 120 volts and the inductor has 60 volts. Now the way to find the effective EMF here, remember that the EMF here is shared across each of them. So as a result, that means to find the final EMF, we're going to apply, so in our solution, we'll say V squared, which is the effective EMF squared, equals V of R squared plus now V of L minus V of C in bracket squared. So this is how we get the effective EMF. So V squared here therefore becomes V of R, that's 30 squared, plus here we're going to be having V of L, which is 60 minus 120 in bracket squared. So V squared equals 900 plus this will give us 60 minus 60. And minus 60 squared is plus 3,600. Okay, so when we add this up, V squared becomes 4,500, which implies that the effective EMF is the square root of 4,500, which will give you 67.08 volts. Now, all the options here are in whole number, so the closest one is 67, which is option B. This particular line of question can come in two forms, so let's kill two birds with one stone. Now, this one says, in an AC circuit, resonance occurs when the impedance of the circuit is. Now, another way to put this question, but be asking a different thing entirely, would be when instead of asking about the impedance, you could be asked about the current. Now, what's the difference between these two? Now, in this case, remember that at resonance, XL equals XC, which implies that if we apply that impedance equals square root of R squared plus XL minus XC in bracket squared, then therefore Z becomes R, because this is 0 and square root of R squared will give you R. So it will be at the lowest at that point. That is, impedance is lowest, is at minimum. Okay, but in the terms of current, the current equals VRMS over impedance. Now, if impedance is low here, once impedance is reduced, what will happen? That is, the current is at maximum. So the effective current is at maximum while impedance is at minimum. So that will be the case. So since this one is asking about impedance, the correct answer to go for is that the impedance of the circuit is minimum, which is option D. However, if it were about current, remember that case would then be for maximum. I hope you get this. Now, this question says, an alternating source is connected in series to a capacitor of capacitive reactance 10 cubed sod 3 and a resistor of resistance 10 cubed ohms. The impedance of the circuit is, now to find the impedance of this circuit, this is what we apply. Now remember, this circuit only has a capacitor and a resistor. So the impedance Z would then be the square root of R squared plus XC squared. So impedance therefore becomes square root of, now the resistance is 10 cubed, so in bracket squared, plus capacitive reactance 10 cubed sod 3 squared. Now let's simplify this. Now this is going to give us square root of 10 raised to power 6 plus, this would give us, now if you square this part, that will give you 3. So 3 times, this one will then give you 10 raised to power 6. That is basically what we're having is 1 times 10 raised to power 6 plus 3 times 10 raised to power 6. Which when we break down, we can then say Z is square root of 1 plus 3, that's 4. So times 10 raised to power 6, which is basically 4 times 10 raised to power 3 in brackets squared. So this one can be written as 2 squared, and square root of this, or basically we just say square root of 4 times square root of 10 cubed in brackets squared. So what do we get from here? Impedance equals, this is 2 times 10 raised to power, square cancel square root, so 3. That is what we have here is 2000. And it is measured in ohms, so the symbol remains. So our answer here is 2000 ohms, which is option B. The power dissipated in an AC circuit with an RMS current of 5 amps, RMS voltage of 10 volts, and phase angle of 60 degrees is, Now, when you're asked to find the power dissipated in an AC circuit, you apply this equation where the power equals IV multiplied by the power factor, and the power factor is cos the angle, phase angle. So now remember that there's an equation for this. So in case if you are not given the angle, like in this case, we are given the phase angle here. So if you are not given the phase angle, you can also apply this part where cos phi equals the resistance over impedance. Okay, so that is, if you have the resistance and you have the impedance, you can use that to find this angle here, the phase angle, the power factor rather, and then you multiply that by current and voltage. But since we are given the angle here, we can easily just solve and say the power dissipated is the current, which is 5 amps, multiplied by the EMF or voltage, which is 10 volts, multiplied by cos the phase angle is 60 degrees. Now power here becomes 5 times 10, that gives us 50, multiplied by cos 60, that is 1/2, and what we have here is 25, and power is measured in watts, so it will be 25 watts, so making the answer option A. The voltage of a domestic electric supply is represented by the equation V equals 311 sine 314.2 T. Now determine the frequency of the AC supply taking pi as 3.142. Now to answer this, we're going to compare. Comparing V equals 311 sine 314.2 T with V equals V naught sine 2 pi ft. Okay, now remember that this 2 pi ft can also be written as Wt. So when we compare this, we can easily see that the peak voltage is 311 volts. So if we are asked to solve for peak voltage in this case, you can easily get your answer as 311.0, but it will be in volts. But this time we are just looking for frequency. So we are going to equate this other side here and say 2 pi ft therefore is 314.2 T. So basically we can say F here is 314.2 T divided by 2 times pi, which is 3.142 times T. So T cancels T, and this would give us this here 1, here it is 100. 100 divided by 2, that gives us 50. So our answer is 50 hertz. So the correct answer here is therefore option A, which says 50.0 hertz. If you're yet to be subscribed to the channel, please take a second to click the subscription button, and you can also hit the notification bell icon so that you get alerted every time we post a new content. And please, if you have any question at all, feel free to ask us. We are here for you. Whether it's on what we are doing presently or it's on something you found during your study time that you would like some help with, please put your questions in the comment section and we promise to reply to all of your comments. So just keep them coming, and please don't forget to like and share the video so that you can help us reach a wide range of audience that are in need of helpful content like this. Now, this question says, in a series RLC circuit, that is a circuit containing a resistor, inductor, and capacitor, at resonance. Now, this is going to be very important to the question, so let's underline it. The voltages across the resistor and inductor are 30 volts and 40 volts respectively. That is, the voltage across the resistor is 30 volts and the voltage across the inductor is 40 volts. Now, what is the voltage across the capacitor? Now, when a circuit is said to be at resonance, what it implies is that the capacitive reactance is the same as the inductive reactance. And what this implies is that the voltage across the capacitor should be the same as the voltage across the inductor. Since VC equals I XC, and VL equals IXL. Okay, and this is a series circuit in the sense that the same current flows through them, and since the reactants are the same, multiply that same current times their reactants, you should be able to get the same amount of voltages. So what this means is that the answer is simply the same amount of voltage that is going through the inductor, and the inductor has 40 volts, so therefore the capacitor should also have 40 volts. So VC is 40 volts, and that is option B. In the AC circuit above, the current value is, now let's add the other details to this. We have 200 volts and 50 hertz source here as part of what makes the diagram. So we see here that the resistance has 30 ohms, while the capacitive reactance, so we can edit this and make it XC, and that is 40 ohms. So to find the current, the same current will flow, which is I. So first thing we want to do is to find the impedance. So let's solve for that first. The impedance Z equals the square root of R squared plus XC squared. So Z here becomes square root of 30 squared plus 40 squared. And this would give us square root of 900 plus 1600. So that is, this is 2500. Okay, so now we can get our impedance as the square root of 2500, which will give us 50, and that is in ohms. Now let's find the current. The value of the current is therefore the voltage or EMF divided by the impedance. So that is 200 divided by 50, and this will give us 4 amperes. So the correct option will be 4.00 amperes, which is option C. At resonance, the phase angle in an AC circuit is, now to get the phase angle is tan phi, and this equals XL minus XC, all divided by R. So since we do not have the angle, or we don't have the value of tan phi, we can then solve phase angle by getting this other side. So basically the phase angle would then be, now recall, at resonance, XL equals XC. So I can then say XL minus XC is the same thing as XL. So all over R. So if we say tan phi equals, this will be 0 over R. So tan phi equals 0. And phi therefore becomes tan inverse of 0, and that will give us 0 as well. So at resonance, the phase angle is 0 degrees, so we go with option C. A capacitor of 20 times 10 raised to the power minus 12 farad and an inductor are joined in series. The value of the inductance that will give the circuit a resonance frequency of 200 kilohertz is, so let's look at what we have. Now we see that the capacitance is 20 times 10 raised to the power minus 12. Inductance is unknown, and then we have resonance frequency as 200 kilohertz, which is 2 times 10 raised to the power 5 hertz. So now we are asked to find L, right? So the equation that joins them says F naught equals 1 over 2 pi square root of LC. Now, when we square both sides, okay, by the time you square both sides, F naught squared would then be 1 over 4 pi squared LC. So from here we can then solve for L by saying L equals 1 over 4 pi squared. Remember, this is also squared. Then C, then F naught squared. So let's solve for that. So L therefore becomes 1 all over 4 times, let's take pi as 3.142, square that, multiply by the capacitance, which is 20 times 10 raised to the power minus 12, and then multiply that by F naught, which is 2 times 10 raised to the power 5. Now all in brackets, then we have to square this as well. Now you can then do the rest of this by using your calculator, but what you are going to get is approximately 1 over 32, right? So from here we can then say the correct option to go for is therefore option D. If you're still not subscribed to the channel, kindly click the subscription button, and you can also hit the notification bell icon so that you can get alerted every time we post a new content. And if you have not downloaded the exam phone app, please find the link also in the description box of this video to download the app today and spice up your learning by using the exam phone app. And please be noted that we still expect your questions. If you have any question at all on what we are doing presently, or perhaps during your study time you came across some kind of questions that you would like some help with, please put them in the comment section, and we promise to reply to all of your comments. So please keep them coming, and don't forget to like, share, and also subscribe to the channel. Now, this question says, the energy stored in an inductor of inductance 5 millihenries, this M here stands for a multiplier times 10 raised to the power minus 3, so it's milli, so 5 millihenry, when a current of 6 amperes flows through it is. Now, to calculate the energy stored in an inductor, we apply that E equals half I square L. So let's solve. This will be 1 over 2 times 6 squared times 5 millihenries. That's 5 times 10 raised to the power minus 3. Now here what we have is 1 over 2 times 36 times 5 times 10 raised to the power minus 3. And 2 here 1, 2 here 18. 18 times 5 is 90, so that's 90 times 10 raised to the power minus 3 joules, which is 9.0 times 10 raised to the power minus 2 joules. So the correct option is B. In an AC circuit that contains only a capacitor, the voltage lags behind the current by. Now, let's kill two birds with a stone. Now, at the beginning of the video, I did mention something. We have what we call the ICE and then ELI. Now, this is for a capacitor only. And it says that current leads voltage by 90 degrees, which is a quarter of a cycle. And this is for inductor, which says voltage leads current by 90 degrees also, which is a quarter of a cycle. So we can then turn this around and say voltage lags current by 90 degrees for a capacitor circuit, and current lags voltage by 90 degrees for an inductor circuit. But in this case, we are looking at a capacitor only circuit, so which means that the current leads by 90 degrees, or the voltage lags by 90 degrees. So the answer here is 90 degrees, which is option B. An AC of 1 amps at a frequency of 800 cycles per second flows through a coil. Now the inductance of which is 2.5 millihenries and the resistance of which is 5 ohms. What is the power absorbed by the coil? Now it's important to note that here we have a resistor and an inductor, And an inductor does not dissipate power, it stores energy. So that is the only one that is dissipating power here is the resistor. So to find the power absorbed there, we have to use the power absorbed by the resistor. So in our solution, we won't be applying impedance, but instead we say power equals I squared R. So the current squared, that's 1 raised to power 2 multiplied by resistance, which is 5, and this will give us 1 times 5, which is 5 watts. So the answer is option A. When the RMS value of a source of electricity supply is given as 240 volts, it means that the peak value of the supply is, now remember, VRMS equals V naught over sod 2. So it means that the peak value is therefore VRMS multiplied by sod 2. That is, we have 240 volts multiplied by sod 2. Now, this is going to give us 339.46 and on like that. So the closest value we have to this is 340. So we're going to take that as our answer. So it's option B. The current through a resistor in an AC circuit is given as I equals 2 sine Wt. Determine the DC equivalent of the current. Now, the DC equivalent of a current when compared to an AC circuit is the IRMS value. So let's find the IRMS value. So first we will compare I equals 2 sine Wt with I equals I naught sine Wt. Now, what this implies is that 2 equals I naught, which is our peak current. And IRMS is supposed to be peak current over root 2. So basically we have 2 over root 2 in amperes. Now you have to rationalize this. So the IRMS value therefore becomes 2 times root 2 over root 2 times root 2 in amperes. And this will give you 2 root 2 divided by 2, which is basically 1 multiplied by root 2 in amperes. So our answer, IRMS here, is therefore root 2 amperes, which is in option B. Now, you can practice and become even better when you use the Exam Fund app. The link to download the app is in the description box of the video. So please click the link, which will take you to either the Google Play Store, the Apple Store, depending on your device, to download the Exam Fund app today. And then you too can get better by practicing with an app that prioritizes your learning time to make it even more exciting. And the beautiful thing about the app is that it's not just a fun app, it is also a rewarding app. That is, you get some money even as you solve multiple questions, just as much as you can do, because it covers a wide range of subjects and topics that will help you do better in your studies. And please do not forget that if you have any question at all, whether it's on what we are doing or it's on something you find during your study time that you would like some help with, please put those questions in the comment section and we promise to attend to all of your comments. So let me use this moment to say a big thank you to you for following the series so far. This brings us to the end of day 36. The series still continues and I will be seeing you in the next video. Bye for now.